Hello and welcome back to the Aquarius software training video series. In this introduction to hydraulic relations, we will be revisiting some of the material that has already been covered in basic hydrodynamics and in rating curve development, a hydraulics-based approach. What we are adding here in this lesson is a little bit more examination of the underlying theory and looking at it, deriving the rating curve a little bit differently, and this may help with resolving some of the more developing an understanding and the solutions for some of the more tricky problems that come up with rating curve development. We're going to start with a review of basic hydrodynamics as a lead into in-depth discussion about the assumptions implicit in a basic stage discharge equation. There are a number of assumptions that we need to make, and we need to really be thinking about these assumptions when we're working within the rating development toolbox. In this way, we can be analyzing our data in a way that will lead to the best possible solution for the relation that we're trying to determine. So, and we will also finish with a discussion of linearizing a hydraulic relation using the concept of plotting offsets. It is a truism in rating curve development that we're talking about steady uniform flow, but what does that mean exactly? And so if we look at our idealized channel with a width W, a depth H, and a channel slope of theta, because we've defined this uniform flow channel to be in a steady state, steady flow condition, that means that the rate of flow is neither increasing nor decreasing at a given moment in time. So that means that the forces driving flow are exactly balanced by the forces resisting flow. Forces driving flow, particularly say pressure potential, are going to be equal to the forces resisting flow, say the channel roughness and the channel geometry. So if we know something about one, we can infer something about the other, and that is very useful for us in rating curve development. If we can accept our steady flow assumption that the forces driving flow are equal to the forces resisting flow, then we can examine this relationship using basic hydrodynamics. So where on the left-hand side of the equation we have the forces driving flow, including factors such as gravitational acceleration, water density, depth, width, and length, and channel slope. On the right-hand side of the equation, the forces resisting flow are the frictional factors, which includes rugosity, viscosity, and sinuosity, and contact factors such as depth, width, and length, and also velocity. Velocity comes in because there's some shear stress that changes with velocity. We can rearrange this equation by grouping. The length component will drop out. Width will drop out if we assume that the width is very much greater than than depth, and we wind up with being able to solve for velocity as the square root of the gravitational acceleration times density times depth times slope divided by our frictional resistance index. Discharge equals velocity times area. From our previous slide, we've determined that velocity is equal to the square root of gravitational acceleration times water density times depth times slope divided by an index of friction. We know that area equals width times depth, and so we can, from this equation, we can make a number of we can simplify it further by lumping things together that are constant. If we assume a rectangular section, then width is going to be constant. Gravitational acceleration can be assumed to be constant, water density, channel slope, and the index of friction. You multiply all those together, you get a global constant we'll call C. That's left with the square root of water depth times depth. You sum the exponents and you have an equation that looks very similar to our rating equation. Discharge equals some global constant times depth raised to the power of 1.5. What we're going to do now is generalize this very basic equation that we've developed for discharge based on depth into a much more pragmatic and useful form, where we have discharge equals beta, which is a product of many variables that we believe to be constant, times stage minus pzh, this point of zero head. Now you can well imagine that if your head drops to zero, that your depth drops to zero at the same level. And so this is one way that we can use what we're actually able to measure and monitor, stage, and relate it to terms that are valuable in a hydraulic relation. So, and then we're going to raise that to the exponent alpha. Now at this point we're not going to specify what the coefficient beta or the exponent alpha are. The values that we're going to find there are very dependent on our on the interpretation of the assumptions implicit in this rating curve. We're not quite done with mathematics yet. From our rating equation, we know that we have to deal with this this exponent alpha. Now logs are mathematical functions that make it easier to deal with power functions. So there's two laws that we're going to be using. One, that log a and times b equals log a plus log b. So, and the other is that log of b raised to the c equals c times log b. What we're going to do now is take these two laws of logs and kind of deal with this exponent in our rating equation. And the way that we're going to do that is going to be by first taking the logarithm of both sides of the equation. So we have the log of discharge time equals the log of everything on the right hand side of the equation. Secondly, we're going to break apart everything that's on the right-hand side of the equation using the two laws of logs. The first law of logs allows us to separate the log of the coefficient as being that plus the log of everything to the right of that. So, and then we're going to use the second law of logs to roll the exponent down in front of the log of h minus point of zero head. So that gives us, at the end of the day, in log-log space, we have a linear relation where we have a line with a slope of alpha, a slope equal to the exponent of our rating equation, and an offset of log of beta. Okay, now we can actually see this equation, what these parameters in the equation look like when we plot them on a log-log scale, where both the stage and the discharge are plotted logarithmically. So if we set our beta value as our coefficient as being 1, our offset value, our point of zero head as being 0, and our exponent as being 1, then we have log q equals log 1, which evaluates to 0, plus 1 times log stage minus 0, which evaluates to log stage. So if log q equals log stage, or basically q equals stage. So we have this beautiful one-to-one line on our logarithmic plot. We can now start to have a look at how manipulating the parameters in our rating equation actually affect our rating curve. So if we consider the red line, the red line represents where we've reduced our coefficient from 1 to 0.5, which has translated the entire curve to the left. The blue line shows where we've increased our coefficient from 1 to 2. It's translated the entire curve to the right. So there's no change in the slope of the curve, obviously, but there is a translation either to the left or the right, depending on whether you increase or decrease the coefficient. Now we know we're starting to develop a better understanding of what the channel variables are that are lumped together into this coefficient. So by understanding this change, this effect that this parameter has on the rating curve, we can start to predict for any given change in the channel geometry whether we would expect the entire curve to be moving to the right or the left. And this predictive power gives us it greatly improves our interpretation of shift corrections. Now we're able to use this mathematical exercise that we went through with logarithms to really start to connect our what we observe in the field in terms of our field visit data through to what we're seeing in a chart in Rating Development Toolbox. Because we know that the beta, our coefficient, carries all information about slope, roughness, and channel complexity. So if we're looking at, say, our photographs of the channel control through time, we may see that the factors affecting roughness have changed through time. So based on what we see happening in the field, we know whether we should be shifting, whether the curve would be expected to move to the right or to the left. And similarly, if we're looking at cross-sectional information, we may see from our field observations that the channel configuration changes at a certain stage, and we would expect the curve to shift to the right or the left above that breakpoint. And so we would introduce a breakpoint into our rating curve to accommodate that point of change in the channel geometry. So these this gives us a lot of power to be able to connect our field observations to our analysis in the Rating Development Toolbox. Now we're going to have a look at what at the power of the exponent in defining a rating relation. If we look at the red line, that shows the a low exponent, an exponent of 0.5, and then the blue line shows an exponent with a value of 2, where your coefficient is 1 and your offset is set equal to 0. So clearly you get far more discharge with a high exponent than you do with a low exponent at the high end of the rating curve. We know from our discussion on hydraulic relations that we expect a head-discharge relation to be linear, but what we're measuring is a stage-discharge relation, so we have to translate from stage into head. Now suppose our sensor for stage is set to some distance above the point of zero flow. Then what we need to do is add that difference in as a constant. And so when we add a constant value to our stage observations and plot them on a logarithmic scale, what we see is that linear relation turns out as being a concave up relation. Similarly, if our reference elevation were stage, we're below the head, then we'd have to subtract that constant value from each stage observation, which would give us a concave down relation. Now, because we're working in a log-log space, there's a really neat little trick that we can do to simplify making rating relations. And that is taking our offset and applying, and rather than adding or subtracting our offset to each and every stage observation, we can just add or subtract that offset to our scale on the ordinate axis. So where our log scale is, say, 1, 10, 100, 1000, etc., becomes 1.7, 100.7, 1000.7, etc. So when we do that, then we can just plot the measurements in their the unaltered stage, and And if we have a true head discharge relation, if we've come up with an offset value that represents a head discharge relation, then we can see our measurements fall into a straight line. So that's really, really powerful, because now we can, when we're, a lot of times we don't really know exactly what offset we should be using. But if we can see that our measurements are falling into a straight line, we can have good confidence that we're in the right ballpark for that offset value. We can now start to consider what the effect of channel shape has on the exponent of our in our rating equation. Where we have a fully rectangular section, we would expect theoretically a slope, an exponent near 1.5. Where we have a fully triangular 90-degree triangle cross section, we would expect an exponent around 2.5. However, natural channels are neither rectangular nor are they triangular. They're always something complicated. So how do you evaluate that? Well, what I like to do is I like to look at the field visit table in my rating development toolbox. Look at the stage column, look at the width column, and just get a feel for how much the width changes as a function of stage. If there's not much change, then obviously you're going to wind up with an exponent less than 2. If there's a lot of change in the width as a function of stage, then you know what, you're going to have an exponent greater than 2. Exactly how much you're gonna develop through experience. You're gonna develop a pretty good feel for what the value of the exponent should be. Now, interpreting the exponent in the rating curve doesn't mean just looking at channel geometry or the shape of the channel. We also need to consider the effect of kinetic energy in the stream. And for that, we find a specific energy curve very useful for explaining the concepts. So the specific energy curve is a plot of the of depth of different stream channels against the energy in that channel. So you can have streams that have the exact same amount of energy occurring at different depths. You can think of a tranquil stream, a tranquil setting where you've got most of your energy is from potential energy, the depth component, and you can think of steep mountain streams where you've got a much lower depth for the same amount of energy, but you've got a lot of kinetic energy. So the curve is defined by all the different streams you could possibly think of, from very steep mountain streams down here to say very flatland kind of streams up in this part of the curve. So what we need to know here is that we'll be talking about critical flow a little bit later and how that plays in. But what we really need to know at this point is that where your stage discharge relation is dominated by potential energy, you can expect this exponent more or less to be somewhere in the 1.67 range. Where you've got a transition where you're starting to get more of the energy from kinetic energy as opposed to potential energy, you can expect an exponent somewhere in the range of 1.67 to 2.5. For critical flow situation, you can expect an exponent somewhere around 2.5. And supercritical flow, you get into exponents greater than 2.5. Now, what we try to do when we're locating our gauges is choose locations where we get a nice potential energy dominated relationship with energy. Because as you can see, for any given change in depth, here we get a relatively small change in energy. That gives us a lot of resolution, a powerful relationship for discriminating between any change in discharge as a result of change in stage. So, but you get into this supercritical flow where it's really the velocity head that's controlling things, and then your stage really doesn't, your change in depth doesn't really tell you a lot, doesn't give you a lot of resolution of the discharge in the stream, because the energy changes so much over just a very narrow range of discharge. So far we've been keeping our offset set to 0, making a stage a direct reference to stream depth. But what happens if stage is set to some datum and not directly related to stream depth? And what if the channel shape is not rectangular? So now we need to look at the role of the offset in the rating equation. We can visualize the role of the offset in how our rating measurements would plot in this example, where if our point of 0 head is above the our gauge 0, then we need to subtract the offset from our stage value, and that renders, where we've got a scale offset of 0, a concave up curve as shown in the blue line. If our point of 0 head is below our gauge 0, then we need to add that offset to our stage values, and that renders a concave down shape to our relation when plotted against a scale offset of 0, as shown with the red line. One way we can come up with what our point of 0 head offset value should be is by trial and error, by manipulating our scale offset until we see our measurements falling into a straight line, as shown with how we've manipulated the scale offset to make our red line from the previous slide into a straight line. Where we have a section control feature, we would expect the difference between the measured gauge height and the gauge height at 0 flow, which we determined from our from observations of our section control feature, to be the rating curve offset. And if we apply that rating curve offset as our scaling offset, we would expect to see our measurements line up in a nice straight line. Now, in a lot of cases, we're dealing with a channel control feature where we can't directly observe what the offset is, but using the same principles, we can use we can work from our scaling offset and manipulate our scaling offset until we see our measurements lining up in a straight line. And when that happens, and we can have good confidence that we're dealing with a hydraulic relation, where we're representing the energy in the stream as a function of stream depth, and that gives us good confidence in building our rating curve. We also have a mathematical method of determining the offset or point of 0 head, and that's often referred to as the Johnson's method. And that's where we start with a couple of discharge observations. We'll call them Q1, Q2, and we'll take the geometric mean of those discharge values to come up with an intermediate discharge we'll call Q3. Now, from a relatively well-defined section of our rating curve, we're going to pick off stage values corresponding to those 3 discharges, and we're going to use this equation here to calculate what the offset should be. Now, this mathematical approach is very precise, but for that reason it can be precisely wrong. It's very, very dependent on having highly accurate discharge measurements and well-defined rating curve to begin with. And often we're not in that situation. Often we have, particularly at the low end of the curve, we often have high measurement uncertainty. And if we're just developing a curve for the first time, often we don't have a really well-defined, we don't have a good idea of what the rating curve should look like to begin with. And so this method is often prone to producing offset values that are unrealistic, that just don't make sense in terms of the geometry of the stream or the hydraulics of the stream. So really the preferred method is to come back from the field with a pretty good idea of what the offset should be, what really makes sense, and have an idea within a fairly narrow range of values. And then within that range of values to manipulate your scale offset until you see your measurements plot in a nice straight line. few things to watch out for is you're using the scale offset graphical method for determining what your rating curve offset should be. Obviously, you're trying to get your rating measurements to fall in a straight line as you approach the correct value for the rating offset. You may need to adjust your rating point placement on the chart as the scale offset displaces the relative position of the measurements, particularly if you're experimentally working through a large range of possible values. It's useful to use the shift diagram to evaluate the scatter around the curve. That's a very useful tool. And be careful about trying to overfit the curve. A certain amount of scatter around the curve is inevitable for two reasons. One, because of differences in measurement uncertainty. You have some good measurements, some excellent measurements, some poor measurements, and that translates into scatter around the curve. The other thing is measurement relevance. The channel control conditions are constantly changing, even in nearly ideal streams, where from measurement to measurement, things will be just slightly different in terms of the control conditions, and so you expect some scatter because of that. And the other thing is that the more time goes on between when a measurement was taken and the control conditions that you're trying to evaluate for, the more you can expect that those older measurements are going to plot further away from the current rating measurement or rating curve. The beauty of using the log-log method for fitting rating curves is that we're trying to fit a simple straight line through our measurements, and as we know, you can fit a straight line through as few as 2 data points, where each additional data point gives you confirmation or verification that the original model estimate is correct. Now that would be ideal if our measurements were without error, but with natural measurements in natural channels, we're always dealing with some uncertainty in the measurements. This uncertainty is the geometric mean of the bias error and the precision error. Bias error is any systematic error causing the value to be either consistently high or consistently low. And precision error is the lack of repeatability of the measurement. Say it's particularly challenging environmental conditions, making it difficult to do for 2 simultaneous measurements to deliver the exact same result. So the more measurements you have, the more degrees of freedom you have in terms of constraining what the possible solution is. But sometimes, even when you have a very large number of measurements, you cannot straighten the plot within these limits of measurement uncertainty. Sometimes you will see some sort of pattern in the residuals in the shift diagram. And that may mean that you've got a multiple control situation where you need a more complex model where it's not a simple single segment rating curve where you might have a multiple segmented rating curve. We'll talk about that next. We can have multiple offsets for multiple control conditions as illustrated in the diagram on the right of the screen. So we can, the offset converts stage to head, and that's what we're really concerned about. So when flow is going through the V-notch part of the weir, then the measure of head that we're interested in is from the very bottom of the V-notch. Whereas once there's so much water that it's pouring over the rectangular portion of the weir, the contribution of the V to the total flow is small, and it isn't really a true measure of how much energy is available for driving flow. So what we want to use that higher sill elevation for the rectangular weir as our effective point of zero head. And so the same situation occurs in natural channels where you'll have the effective point of zero flow is being somewhat above the true point of zero flow for open channel conditions. But once the stage drops to where there's water being channeled between rocks on the in the stream bed, then you need to get down to describing the curve with respect to the true point of zero flow. Multiple offsets can be used to straighten different parts of ratings. In this example, we have a channel that transitions from a section control, slope of 2.5, point of zero flow of 0.3, to a channel control, slope of 1.67, point of zero head of 0.6, with a transition through a stage of 3.0 meters. When we're working with a curve with multiple rating offsets, we need to be very careful about our selection of scaling offsets. So in this case, I've set just a single offset and then plotting to that single offset, which is valid for the lower segment of the curve. Because I should be using a different rating offset for the upper segment of the curve, I should be using a different scaling offset for viewing the upper segment of the curve. So we'll look at that next. In this case, I can add my second rating offset, which is valid for the upper segment of the curve, and I can plot to that second scaling offset using the offset 2 option. So now the upper segment of the curve is plotting correctly, but my lower segment of the curve, which should be plotted to a scale offset of 0.3, is going to be somewhat distorted. Now I can display both segments of the curve correctly using the multiple plotting offsets option, and that will display the lower segment using the offset 1 and the upper segment using offset 2. But notice that there will be a breakpoint, a discontinuity at the where the two segments join. In most situations, we would not expect a transition suddenly from a section control to a channel control situation. There is more typically a smooth transition from one to the other. And so adding additional rating points through this transition zone can make a more realistic looking rating curve. It's quite typical that ratings must be extended outside the range of gauging measurements, and so we'll have a look at some of the methods used to extend rating curves. AQUARIUS is a handy little tool for extending rating curves. It uses the same slope and offset, and so it's based on the same hydraulic principles and allows you to extend the rating curve. However, because you are assuming that the hydraulics are valid, you should not use this method to extend above where the channel configuration changes, say above bank full. For those sorts of situations, you're going to probably want to resort to some field methods, such as the slope conveyance method or the step backwater measurement, where you go out and do some additional surveys to determine what the peak discharge likely was to correspond with your peak stage from your recording gauge, and that will give you some confidence in terms of where the top of the rating curve should go. You may want to use some flood routing techniques using upstream or downstream gauges, and you can use empirical modeling toolbox for that. Or you might want to use peak runoff rates from nearby hydrologically similar gauges, and again you can use some empirical modeling types of approaches to determine what a reasonable estimate of the peak discharge is that you can associate with your peak stage value. The use of the curve extension tool in AQUARIUS really works quite well because we've taken some care to make sure that we've correctly identified our offset values. When offsets are used correctly, we're talking about a hydraulic relation, and it's quite reasonable to extend a hydraulic relation as long as we understand something about the control conditions and the cross-section configuration. This is different from if you're just fitting a curve by eye through a scatter of points or using a statistical method where your confidence in extending a curve would be much, much lower. We've had to make a number of simplifying assumptions to be able to use principles of hydraulic relations to derive a rating curve. But the real world is never quite as simple as would be required by these assumptions that we've made. So in the next lesson on natural channel controls, we're going to be talking about how we can accommodate some of the complexity of natural channel controls and how those controls are continually evolving over time. I'd like to thank you for your time, and I certainly hope that this information has been useful for you. I hope that it will improve the quality of the ratings that you develop. I hope that it improves the efficiency with which you can develop and interpret rating curves. But this information is by no means complete or exhaustive. We have some other training material that you may want to refer to, such as basic hydrodynamics, natural channel controls and ratings, and a hydraulics-based approach to ratings. Thank you. We've covered an awful lot of information from basic hydraulic theory right through to practical applications using AQUARIUS, and it might be useful for you to go back and review some other material provided in these from these websites on developing ratings to develop a broader perspective on how to interpret data for developing rating curves.